Factorial of any number n is defined as n factorial equals to n minus 1, n minus 2, to 1. For instance, the 5 factorial is equal to the multiplication of 5, 4, 3, 2, 1, and this equals to 120. Now, notice that 5 factorial is equals to 5 times the 4 factorial. And this relationship allows us to define the factorial function recursively. If f of n equals to n factorial, then I can also write f of n as n times f of n minus 1. However, the domain of this function is restricted to positive integers, and this makes fn discontinuous, as it is only defined as discrete points. But the question is, can we extend this definition to a more generalized function, where n can take any real or even complex value? For someone unfamiliar with such a continuous function, this idea might seem a little mysterious. But to find a formula for f of n that works for all real or complex n is a fascinating challenge. Let's revisit the factorial sequence to investigate further. Interestingly, factorials naturally appear when we differentiate the functions which has the form of x to the power n. For instance, if f of x equals x to the power 5, then differentiating this function 5 times with respect to x yields the value of 5 factorial. In general, I can get n factorial when the function x to the power n is differentiated with respect to x n times. This relationship is only valid when n is a positive integer, isn't it? So, I think we have to consider a different function. Maybe f of x equals 1 by x. Now, if we differentiate this function repeatedly, an intriguing pattern emerges. After n differentiations, the numerator of the result takes the form of n factorial, with the alternating signs depending on the value of n. And this suggests another connection between differentiation and factorials. And this relationship becomes even more elegant when we use the integral form. Consider this integral, which also gives the function 1 by x. If I differentiate both sides with respect to x, the equation becomes quite interesting. Notice how the negative factor cancels out from both sides. Now, differentiating the function, the f of x or this integral, n times would yield the value which is proportional to n factorial. Now, evaluating this equation at x equals 1, we obtain an equivalent form of n factorial expressed in integral form. And this is famously known as the gamma function. The beauty of the gamma function is that it generalizes factorials to any real or complex value of n.